All right. Hello, everyone. My name is Jonas, and I work on debugging at Apple. And today I want to talk about WebAssembly debugging in LLDB.
Sorry, a little bit loudly, please.
Louder?
Yes, please.
OK, I'll do my best. The speaker also kind of echoes. All right, so this work was primarily motivated by Swift. And targeting WebAssembly from Swift has come a long way. It started originally as a community project. Akio created WAMR as an open source project in 2018. And it was the first WebAssembly runtime written in Swift targeting Swift. And then a few years later, Max, who may or may not be in the room, there he is, he took over maintainership of the project and he renamed it to WasmKit. After that, Yuda, he interned at Apple, and together with Max, they got 100% spec test coverage for WebAssembly with WasmKit. And then with the release of Swift 6.0 in 2024, embedded Swift targeting WebAssembly became an experimental feature. And also in Swift CI, we adopted WasmKit to test the targeting to the compiler support. And then last year, in 2025, all their hard work culminated in WebAssembly being officially supported as of Swift 6.2, and WasmKit now ships as part of the toolchain. And of course, all of this is open source. I know the kit at the end might be kind of confusing. The runtime is developed under the Swift Wasm organization on GitHub, and of course, the compiler support is just in upstream Swift. And if you want to learn more, check out swiftwasm.org. So our goal for Swift compiled to WebAssembly is to provide a first-class debugging experience. And that means full source level debugging, where you can set breakpoints, step in and over Swift code, and of course, show your variables. And so in order to achieve that, the debugger needs to know about the Swift programming language, which means that there's two approaches. One, we could teach existing tools to debug WebAssembly and teach it about Swift, or we could teach LLDB, which already knows about Swift, about WebAssembly. And so maybe the first approach sounds simpler on the surface, but it really isn't. Debugging Swift is far from trivial, and LLDB already has years and years of investments in that space. On top of that, if we add WebAssembly support to LLDB, that doesn't just benefit Swift, but pretty much every language that is supported by LLDB. And that's why we thought that was the better approach. So before we commit to any approach, I do want to compare a few options that exist for debugging or existed before I started all this. And we identified three main approaches, each with their own pros and cons. And an interesting observation here is that they all use LLDB one way or another. If you've played around with WebAssembly, you're probably already familiar with WasmTime. It is the reference implementation of the WebAssembly runtime, and it's developed by the Bytecode Alliance. It uses just-in-time compilation to generate native machine code with debug info. And so debugging on WasmTime means debugging the runtime, and the JIT code just runs as part of that same process. And so you can debug WasmTime this way with either GDB or LLDB. And to the debugger, it just looks like you're debugging native code. And so what's neat about this approach is that no changes necessary. LLDB doesn't need to know about WebAssembly at all. The trade-off, on the other hand, is that you are debugging the runtime. And so it can make it kind of hard to distinguish between runtime code and the code that you're trying to debug. For example, if you're looking at a backtrace, you're going to get all these frames coming from the runtime that you have to mentally filter out. Chrome takes a different approach. They have a DevTools extension, which adds support for debugging C and C++ code right from within the browser's built-in developer tools. And this extension also uses LLDB under the hood, and it uses that to parse dwarf and create types, but pretty much everything else is done by the browser itself. And so as a developer, that's nice because you can use the same tools for debugging JavaScript as you do for WebAssembly. The downside is for Swift support or any other language, you need to extend the browser and teach it about it, which is one of the things we wanted to avoid. The third approach is the WebAssembly Micro Runtime, sometimes abbreviated as WAMR. It is also developed by the Bytecode Alliance, and it's a lightweight standalone runtime targeting embedded and IoT applications. And this has a small debug server that talks to the GDB remote protocol, which is an industry standard that's supported by both GDB and LLDB, despite the name. It's also the approach we started pursuing, and the debug step in the micro runtime meant that we had something that already existed and we could work with. So at this point, you're probably curious what this looks like. So I'm going to jump straight in with a demo and show you what it looks like before I talk about the boring implementation details. So hopefully that's not too small, but I realized that I might have underestimated the size of the screen. So there's a short recording of Swift, which is compiled to WebAssembly, and we're using LLDB in Visual Studio Code to debug it. The code is fairly trivial, especially for the people in the back. We got a dictionary mapping some fruits to prices, and then we have a kind of contrived function that just adds entries to the map. So I'm going to start playing the demo. So I'm going to set a breakpoint here, and then I'm going to run. I already compiled this, and you can see we got a backtrace, exactly as you would expect. Then we have local variables. I can show you this is the input to the function arguments. Then I continue, so you're going to see the values changing because we're in the next iteration of this function getting called. And I'm going to continue stepping out of it. Here I'm just proving that those values look the way you expect. So I continue, or I step out of it, and then here's the fruit prices variable that we can also inspect. And so far, everything just looks like native debugging. So to prove to you that this is actually debugging WebAssembly, I'm doing a disassembly here to show you all the instructions. But in order to get here, we had to build several key pieces. So let me talk about that next. One of the key design decisions was using the GDB remote protocol. So I want to start out with an overview of that architecture. So in a native debug session, LLDB uses a client-server architecture where the client is LLDB itself and it runs on the host. And then it communicates with a debug stub, which runs next to the program you're debugging, which we call the inferior. The stub is a lightweight entitled binary that directly controls the inferior. And usually it does so with help from the operating system. For example, on Mac OS and Linux, that's going to be ptrace. And also I want to call out that the same client-server architecture is used regardless of whether you're debugging remotely or locally. In the local case, like the host and the target are just the same machine. The GDB remote protocol is simple, it's well documented, it's widely adopted, and it's also supported by a bunch of tools, including LLDB and GDB. And I realized that this year it has existed for 40 years, so it has really proven itself, which is the reason we want to build on top of that. So here's what that architecture looks like for WebAssembly. Here the runtime would implement the GDB remote stub, and how it does that is entirely implementation defined. Different runtimes can choose to optimize for their own constraints. And then just the normal way, LLDB will talk using the GDB remote protocol to the debug stub, and that way control the WebAssembly inferior. And the key takeaway here is that this approach provides a standardized way for any debugger to talk to any WebAssembly runtime that exposes the GDB remote protocol. And the nice thing here is like LLDB doesn't need to know about the implementation of the runtime, and the runtime doesn't need to be aware of the debugger debugging it. And also, WebAssembly is modeled around a stack-based virtual machine. And as we'll see later, that poses some concepts that can't directly be translated into concepts in the GDB remote protocol. And so this requires a handful of extensions that both the runtime and the debugger need to support. Luckily, the protocol was always designed to be extensible, and the majority of the packets are all standard. So let's take a look at the implementation. And previous to this work, LLDB already had some Wasm support, in particular for the Chrome DevTools integration that I mentioned earlier. It supports reading Wasm binaries, loading them into memory, and then using the dwarf to create types. And the micro runtime as debug stub was also designed to work with LLDB. The repository contained a patch which was based on work from Paolo Severini. He was the driving force behind some of the earlier existing WebAssembly support in LLDB, and some of my work is a continuation of some of the PRs he put up there. And we also made it a goal to remain compatible with the debug stub in the micro runtime. During this process, we encountered some places where we might have taken some small different design decisions, but nothing that warranted breaking compatibility. All right, object files. So the first challenge here was that LLDB's existing object file Wasm plugin was rather rudimentary. To keep things simple, we were looking for a handful of known sections and ignoring everything else. And we needed to expand this to read arbitrary sections. In particular, Swift has some metadata, or language-specific metadata sections that we needed to read. And most of the work was reading the spec, knowing how to parse those data sections. WebAssembly generally follows the ELF model, where sections contain segments. But one interesting thing is that those segments can be active or passive. And active segments are automatically loaded into memory during module initialization, and they use what's called an init expression to specify where. And this init expression consists of a series of Wasm operations, or a subset of them, which meant that we had to implement a tiny Wasm interpreter in our objects file plugin, which was a fun exercise, as you can imagine. The next challenge was supporting symbols, and for that we needed a symbol table. But WebAssembly's concept of a symbol table is exclusively used for linking, and it isn't preserved in the final binary. But Wasm does provide something called a name section, which is one of those new sections we had to parse. And the name section contains the function names and an offset, or actually an index, into the function section. And the function section contains an offset into the code section together with a size. And I think that's it. And so we had to combine all of this together, the name, the size, the offset, and then populate LLDB's concept of a symbol table. And so with that, you can now set breakpoints by symbol name, even if you do not have dwarf debug information. Now we can set, so we have a symbol table, we can set breakpoints, we can run to them. The next thing you want to do is be able to see where you are. So for that, you do the bt command. And so normally, LLDB would examine the frame pointer register and then walk the stack. But doing unwinding depends on concepts such as registers and an ABI-defined stack layout, and these things just don't exist in WebAssembly. So for native code, LLDB has to do the unwinding ourselves, but we realized that for WebAssembly, we can rely on the runtime, which already needs to know this information. And this brings us to our first extension packet to the GDB remote protocol. It's the QWasm call stack packet, and this queries the runtime for a list of program counters representing the call stack for the current thread. LLDB then symbolicates it using the information from the symbol table or from the dwarf debug info, and then you get the backtrace as you would expect. Next up is variables. For that, we need a little bit of background about how debuggers use dwarf to parse debug information. If you were in the talk this morning about dwarf 6, you might have already been prepared. So the debugger uses dwarf location descriptions to find and recover variable values at runtime. And these things can take several forms. So they can be empty in case the value is unavailable because the variable has been optimized out. They can be implicit when the value is known, but there's no runtime representation, something like a constant. If a variable lives in memory, you have a memory location and we get an address. And if it lives in a register, we have a register location and we get a register name. Empty and implicit locations work exactly the same way in WebAssembly as they do for native code, but memory and registers behave slightly differently. WebAssembly doesn't have a concept of registers, and so therefore no register location descriptions. However, WebAssembly has a few other places where it can store values, namely locals, globals, and an operand stack. And so to handle those cases, WebAssembly uses something called virtual registers, which is entirely a debugging concept, to describe this in dwarf and have the debugger query the runtime. So when a value is stored in a WebAssembly local, global, or along the operand stack, if we use a dwarf vendor extension called DWOP Wasm location, it takes two arguments, the first one specifying which one of these three it is, and the second one specifying an index like the first or the second or the third global. Each register also has its own corresponding GDB remote packet. These are also extensions that the debugger then uses when it encounters it to query the runtime and get the value back out. So let's look at an example for a function argument. And so in native code, depending on the ABI, you might expect that to be passed in a register and get a register name. So in WebAssembly, we will get a dwarf location description that uses the DWOP Wasm location. And so in this particular case, the value is stored as a function local at index 2, so the second function local. So when LLDB encounters this, parses the dwarf expression, it encounters this, and then it's going to query the runtime with a Q Wasm local and index 2. Gets the value back, and it shows it to you. Variables located in memory behave pretty much the same and can use dwarf standard memory locations, but WebAssembly's architecture requires a little bit of care. Specifically, WebAssembly follows a segmented memory model where code and data live at separate address spaces. Also, different modules each have their own address space. And LLDB doesn't currently have address space support, which is something that's come up a few times today. So we needed a creative solution. And what we did is we used the top 32 bits of a 64-bit address to encode the address space. We use the first 2 bits for the type, so like code or memory, and then the remaining 30 bits we use to encode the module. And so this approach works well for 32-bit Wasm, which is still very much the default. But obviously for Wasm 64, we'll need all 64 bits for the address, and we will need to come up with something different. Luckily, this address space support in LLDB is something that we've been discussing on the forums. I need to hurry up. Although Swift uses dwarf as its debug info format, for anything but trivial types, we also need the Swift reflection metadata, for example, to resolve the concrete type of a generic at runtime. And so Swift uses a common library, libswift reflection, and it's used at runtime for performing reflection, and it's used by the debugger to generate types. And so what that means is it's nice to have one implementation so we don't have to duplicate the code. What that means is that this library also needs to be able to parse those sections I mentioned earlier, and so we had to redo some of that work in libswift reflection. But the thing is that this was pretty much all it took to support Swift, because all the other things are built on top of the primitives provided by the GDB remote protocol. And we also didn't need to modify the runtime or anything to make this all work. Finally, we introduced a WebAssembly platform to LLDB. And so when you create a target in LLDB with a WebAssembly triple, this platform will automatically get selected. And so one of the responsibilities of the platform is launching binaries. And this platform can be configured with a specific runtime so that when you load it in LLDB and you type run, it's automatically going to launch that under that runtime, connect to the GDB stub, and make it look like you're just debugging something natively. And once configured, like this thing disappears and you get the user experience that you're used to. So with all that, I'm happy to say that I think we delivered on our original goal, and LLDB now has first-class debugging support for WebAssembly. And not just for Swift, but for any language that is supported. We also succeeded in building a solution that's not tied to a particular runtime. We have already 3 runtimes today that support debugging with LLDB this way. So besides the Micro Runtime and WasmKit, there's also support in WebKit's JavaScriptCore engine. And so all these runtimes support the protocol extensions that I've discussed earlier. They are formally documented on the LLDB website, and I hope to see more debuggers and runtimes adopt them. So what's next? The immediate priority for us is to extend our test suite to build all our test binaries for WebAssembly and then run them under a runtime. That's going to allow us to reuse our thousands of existing tests to test our WebAssembly support. And hopefully this will also help uncover bugs in the different runtimes GDB stubs. And beyond that, we'll want to support more Swift features as they make their way over to WebAssembly. And then address spaces is something we'll need to do in order to get Wasm 64 support going. I want to thank everyone that made it possible to make this happen. Paolo for his work on WebAssembly and LLDB, Adrian Prantel for his work on the Swift parts, David Spickett for reviewing my PRs, Mex and Yuda for their work on the WasmKit, and Yija, Sho, and Mark on the WebKit team for adding this to JavaScriptCore. Thank you. I think there should be a little bit of time for questions.